Hello everyone, welcome back. Imagine you are looking for a word in a dictionary which contains words in a sorted order, A to Z. Do you start from page 1? No. You open the middle, check if the word is before or after, and repeat the process again and again till you find the word. This is the core idea of binary search. Now, what if we applied this logic to tree-like data structure? That's exactly what a binary search tree does. So in this video, we'll understand what is binary search, and using that concept, we'll understand what is binary search tree and what is the complexity of searching in a binary search tree. So let's start. Let's understand the binary search concept. Imagine that we have given an input numbers like this, and these numbers are present in a sorted ascending order. Now we have a task to search 38 number in these numbers. So initially what we will see that the search space, basically we need to start from 0 till end, which is 10th index, to find number 38 in a normal scenario. But binary search algorithm uses the fact that the input data is already sorted. So how can we reduce this search space? So what binary search algorithm does is it finds out the middle element. So middle index is calculated like start plus end divided by 2, which is 10 by 2 equal to 5. So once we find the middle element, which is 23, we check whether the number which we are trying to search is greater than or less than the middle. If it is less than, then it will be definitely on the left side of the middle element because the number is less than the middle, and because the input is sorted, so it will be on the left side. But if the number which we are trying to search is greater than the middle, then it will be on the right side of the middle because the numbers which are greater than middle are on the right side. So using this fact, we divide the search space here. Now 38 is greater than 23. So the new search space where we will try to find the 38 is start equal to middle plus 1, which is 6, to end 10, because the middle element was 23 and 38 is greater than 23. So we are checking on the right side of the array where greater numbers are present. Now we again check the middle element, which is start plus end divided by 2, 6 plus 10 divided by 2 equal to 8. The number is 57. Now 38, the number which we are trying to search, is less than 57. So it is definitely present on the left side of the middle because the numbers which are less than middle are on the left side of the middle. So we reduce the search space again. Start is 6 only, which was previous, but end is now middle minus 1 because the number 38 is less than 57. So it will be on the left side. Now the end is 7. So we reduce the search space. We again find the middle, which is start plus end divided by 2, which is 6 plus 7 divided by 2 is equal to 6. Now we find the middle element. We again check whether the number which we are trying to search is less than or greater than middle. In this case, it is equal to middle. So we found our number. So the current middle element is 38, which we are trying to search, and we have completed the search. So in a binary search concept, if you observe this, it is reducing the search space in every step by half. How? Using the middle element. Because the input is in a sorted order, the number which we are trying to search, we can easily divide the search space into half by checking or comparing the number which we are trying to search with the middle element. Because that way we can search either on left or on right if the number is less than middle or if the number is greater than middle. So this is the binary search concept. Let's understand the requirements for binary search algorithm to work. First requirement is that our input data should be in a sorted increasing or decreasing order. Why? Because when we check the middle element, if the data is not sorted, then we will not be able to decide whether to go on a left side or on a right side and divide the search space in a half for every space. That will be difficult. That's why if the data is unsorted, then we need to sort it first, then only binary search algorithm will work properly on that input data. The second requirement is random access allowed, index based access. So binary search works best on arrays, not linked list, because it requires a direct access to the middle element. We need to find the middle element. Then only we can divide the search space by going to the left or going to the right. And that we need to do in a constant time. But in a data structures like linked list, which do not provide a random access, we need to traverse the list to find the middle element, which can add more time complexity to our binary search algorithm. And it makes the binary search inefficient in such cases. The third requirement is no frequent insertion or deletions. If the data set is dynamic with frequent insertions or deletions, maintaining that sorted order becomes costly because we can only apply binary search on sorted data. The next requirement is data should not have too many duplicates for optimal performance. Binary search we can use with array having duplicate elements or the data having duplicate elements, but it will require extra logic. Why? Let's say we find the middle element, but middle element, the value which middle element have, if there are many elements with the same value, then we need to have some extra logic to decide from where we need to start searching again, on left side and on both right side. So that extra logic we need to write, which makes binary search less optimal. Now we understood the concept of binary search. Let's understand how that concept is applied on a binary tree and how it becomes a binary search tree. Binary search tree is a tree-like data structure where each node follows two rules. Left subtree contains values smaller than the node, and right subtree contains values greater than the node. Let's understand with the example. Let's say this is our node, which value is 50. If you see the left subtree or the left nodes have a smaller value than the node, 30 is less than 50, and right subtree, which have value 70, is greater than the value 50 or the node. Similarly, it is followed for each node in a tree. For a 30, the left subtree is having value 20, which is less than 30, and right subtree have a value 40, which is greater than 30. For 70, again the same rule is followed. Left subtree contains smaller value than 70, and right subtree contains greater value than 70 node. So this is what is a binary search tree. It is a special type of binary tree where each node in a tree follows these two rules. So this structure allows us to apply binary search logic in a tree form. Instead of searching through a list, we navigate left or right. For example, if we want to search 40, in normal binary tree, we will search whole tree. But in a binary search tree, we can divide the search space in a half for each step, like how we understood in a binary search concept. We'll understand in more detail in a next slide. Let's understand the time complexity for a search operation in binary search tree. Let's say this is our binary search tree, and if we want to search 40 in it, we will start from the root, which is 50. Now 40 is less than 50. So because the smaller values will be on the left subtree side, so we'll go to the left. So what can we see here? We don't need to worry about the right subtree. We just need to check for a left subtree. So we reduce the search space here. Next step, 40 is greater than 30. So we need to check only in a right subtree. So the search space is reduced to only this. In the next step, the node which we are trying to check, which is 40, contains the value 40 which we are trying to search. We found the 40. So what did we observe? For every step, search space is reduced by half. Why? Because we know that in binary search, for every node, left side contains smaller values and right side contains greater values than the node value. So we use that fact and apply the binary search. And for step 0, we started with all nodes of the tree. And once we check the value which we are trying to search with the node value, then we see that we just need to go on to the left side. So we reduce the search space n by 2, which is 7 by 2 equal to 3. In the next step, we check 40 is greater than 30. So we just need to go on to the right side. So we again divided the search space, n was 3, so 3 divided by 2 equal to 1. So the fact that for every node, smaller values are on left side and greater values are on right side. So that fact is used to apply the binary search algorithm. And we continue until only one element remains. So if we put it in a formula, so n is the number of nodes in a tree. We divide it by 2 raised to k till it becomes 1, because we need to find till there is only one element which is matching to our search, the number which we are trying to search. And k is the number of steps here, because for every step we are reducing the n by 2. Now if we take this 2 raised to k here, n is equal to 2 raised to k. And if we apply log on both the sides, so you can see k is equal to log of n with base 2. So this is the time complexity. So log of n is the time complexity for search operation in a binary tree. So if let's say n is a 7 in this case, so how many times we need to traverse? Log of n, which is log of 7 is 3. Step 1, 2, 3. Only 3 times we need to check. So this is the search complexity. But this time complexity is not true for all cases. In this case, binary search tree is not skewed. So that's why we can say the time complexity is log of n. But if we have a binary search tree like this, which is a skewed, right? And we try to search, let's say 4 in it, then we need to still parse or traverse all the nodes of the binary search tree to search 4. So in a worst case, we can say the time complexity in binary search tree is O of n, because we need to check all the nodes of the tree. So in a best case or average case, we can say log of n, but in a worst case, it will be O of n to search any number, because in worst case, we need to check all the nodes of the tree if the tree is a skewed tree like this. So in this video, we understood about the binary search concept using examples, and we also understood how that binary search concept is applied on a binary tree data structure, which then becomes the binary search tree. And we understood what is the structure of binary search tree, like basically how it follows the rules for left subtree and right subtree, so that binary search can be applied very efficiently. And what is the time complexity for searching any data in binary search tree for both best case and worst case. So hope you understood the explanation. If you like the video, please share and subscribe. Thank you so much.